Hello everyone, welcome to another video of From Concept to Circuit. In this video, we are going to explore beamforming using ADALM-Pluto. In this setup, as you can see, we have two TX channel in one ADALM-Pluto and receiver is another ADALM-Pluto, and what we are looking at is how as we change the phase of the one of the TX channels, how is the received power change at the receiver. Basically, we are seeing at which phase we can receive the maximum power at the receiver, meaning that this is the phase that the two TX signals are receiving at the same time, so they add constructively. First, we are going to look at the idea of beamforming and how it helps and explore some math behind it. Then we are going to look at how we can enable ADALM-Pluto second TX or RX channel for beamforming. Then we'll go over the code. Okay, what is beamforming? Beamforming is using the wave behavior of electromagnetic waves to add them constructively in the points that we are interested in to create a beam when we are transmitting a signal from a transmitter to receiver. This is advantageous because we can use that beam to steer the beam without steer the direction of transmitting without physically moving the antennas. We can just change the phase relationship between the channels of the transmitter, or if we have at the receiver we have several phase array antennas. By just changing the phase relationship between the channels, we can steer the beam without physically changing it. Also, if we add them constructively, we by adjusting the phases of the channels to the point that we are interested in, we can increase the gain and directivity to that point that we are interested in. For instance, in this example, I have two TX antennas and one RX antenna. The idea is if by changing the phase relationship between these two TX antennas, I can maximize the power of the received signal at the receiver so that my gain when transmitting from the TX to RX is increased compared to using just without beamforming, where the electromagnetic waves are propagated spherically. So yes, as I mentioned, basically the idea is we want to create a beam with the direction that we are interested in uh, by changing the phase relationship of the antennas so that the waves at the receiver at the point that we are interested in add constructively. This can be adjusted basically by changing the time relationship of the transmitted signals, which in a given frequency, it's also transferable to phase relationship of between these two. So basically, what we can do is that in the when we want to initialize a transmission, we can we can sweep the phase or time or delay relationship of the channels to maximize the delivered power at the receiver. And basically, this is to make sure that we at the receiver the waves arrive at the same time, so they add constructively. But how we can ensure that the waves are arriving at the same time? Basically, if we can look at here, as I mentioned here, assuming that we have far field conditions, we have these planar waves here, and you can see that signal from TX2 has to travel a further distance compared to TX1 to reach RX. How much is it? If I add a parallel line to the wavefront at the receiver, I end up with this with this distance of L, meaning that the signal from TX2 needs to travel L, it is traveling uh, further by amount of L before reaching at the Rx. And by some mathematical equations, I can find out if I have the theta, which is basically the steering angle defined between the line that I draw from TX2 to RX and the horizontal axis, I can define L equal to d sine of theta. And basically, I just need to find out how much is L in terms of time, so that I just delay my TX1 by that amount or fire TX2 uh, delta t times delta t sooner, so that as the waves are traveling, when they receive at Rx, they add constructively. Using having L, I can find delta t by just dividing L by c, which is the speed of light, and this is in terms of time. I can also find delta t in terms of phase by just having the lambda of the wave at the given frequency. So basically, this is the equation we have for beam forming and steering the wave that we can use to create a beam forming transmission. We are going to use our ADALM-Pluto to create a very basic beamforming in this video. But as we understand the behavior and the fundamentals behind the beamforming, we go over the more advanced examples in future videos. For instance, we can use the idea of beamforming and use also multiple channels at Rx to find out what's the arriving angle of the signal and other properties. But to just not make this video long, we just want to um, explore the idea of having two TX channels and one RX channel and see if we change the phase between these two TX channels, what is the received power at the receiver. Before that, I just want to also go over the idea how we can make beamforming. Because as I mentioned, we need to create a delay or a phase difference between our TX channels or RX channels when we are making beamforming. But how can that be done? Is either we can add that, either we can create that phase mismatch at a high frequency when after our mixer where the signal is at high frequencies, or we can create that delay or time mismatch at a baseband before it's up converted to higher frequencies. This is definitely a design choice. Each one has its advantages and disadvantages. We'll make sure to go over that and also see how integrated circuits the circuits for those are made. But for now, just we want to just understand that the beam forming can be either in high frequency side or low frequency side. In high frequency side, basically after the signal is up converted, assuming that both channels have equal phase between each other, we can add a time delay or a phase shifter here to change the phase of one of the channels. But definitely this requires more advanced circuitry because we are dealing with higher frequencies. Whereas we can add the phase or time mismatch in the baseband, basically by changing the DAC signals when they are generating the baseband signal. So here we are just looking at one channel, but you can see that in AD9361 we have two TX channel, same behavior. So basically, if you want to generate baseband differences. Each of these, so we just change phase relationship between the channel 1 and channel 2 uh, when we want to send the data to the DAC to create to the signal. Okay, so before moving on to the code, I just want to also show how we can enable second transmitting and receiving channel in ADALM-Pluto. Basically, ADALM-Pluto by default is configured in such a way that only one channel is at the output because as you can see at the package, it's only one TX and one RX channel. The second channel, for accessing the second channel, we need to open the package uh, and we need to have a Pluto SDR Rev C and later to get access to the second channel. And also we need to change the some of the firmware settings of ADALM-Pluto. First, we need to go over this website to update the firmware, then another website that has some instructions for enabling the second channel. So let's go and see how it's done. Okay, first step, we need to go to this website. I put the link in the description, in the video description. But basically, this is a website that you can go and download Pluto firmware to get access to latest Pluto firmwares through GitHub. So if you come to this website, you can see latest ADALM-Pluto release. And if I go to this um, GitHub, I can see the latest firmware is 0.39, and you can see the summary of what's new in this firmware. And if you go down, you can find a zip file for Pluto SDR firmware version 0.39. I've downloaded this zip file and extracted it. This is the contents of the zip file. Basically, the idea is very simple. If you want to update the firmware of Pluto, as you extracted this, uh, you need to just move these files to the ADALM-Pluto USB drive when it's connected, and just eject the USB. I don't know if like all of the files are required to be moved here, but I just do it this way. Just move it here. They get copied to my Pluto SDR USB. Then here I come and eject Pluto SDR. Then what happens is that as you eject it, it takes the LED at ADALM-Pluto starts blinking very fast. You need to give it time to update the firmware, and if once the firmware is done, it uh, the device gets connected back again. Okay, now we move to customizing the Pluto configuration website. I'll also put the link for this website down below. So this web page is uh, very good if you want to explore different configurations for ADALM-Pluto. For instance, assign a different IP address to your ADALM-Pluto. But what we are interested in is first we want to configure our uh, firmware basically to AD9361, which is uh, you can see the difference between 9361 and 9363 is basically wider tuning range, bandwidth, and 2TX and RX channel. One interesting thing is that you may say, okay, so how is it that we have this AD9363 in ADALM-Pluto, but why we can change it to AD9361? Basically, I think one of the ideas behind these ICs different naming is that it's just probably the circuitry inside them is not different from each other. It's just that, as you know, as in when you send the IC for tape out, due to some uh, non-idealities in the tape out process, you sometimes do not get what you actually made. For instance, you have an oscillator in your IC which needs to support 70 megahertz all the way to 6 gigahertz, but once the IC comes back from 100 of the fabricated ICs, 90 of them can go and support that range, but tens of them don't. What basically these you can say that these are skewed corners. The skew can be due to several non-idealities. For instance, different uh, uh, silicon behavior, silicon properties between between the dies. But this is beyond the scope of this video. But my thinking is that basically for the ICs that have uh, some of these skewed behaviors, they just say we don't guarantee this 70 to 6 gigahertz uh, performance, and they limit the performance to 300 to 3.8 gigahertz. But definitely by changing the firmware, you can break this limit. And if I go down here, you can actually see also an instruction of how to enable to receive and to TX channel in your ADALM-Pluto Rev C and later version. Basically, the second TX and RX channel, as you can see in the window, um, it's a UFL connection inside in the PCB, and to get access to it, you need to open the lid of the ADALM-Pluto, either create a hole and uh, bring out that connection to the edge of the package, or like me, just connect it directly. But I plan to create a better connection and bring the second TX and RX channel to the edge of the board. So I just need to do this to enable second TX and RX channel. For that, I will use PuTTY to get connected to the device and uh, send these commands. Okay, now let's use PuTTY to connect to the ADALM-Pluto and change the firmware to enable second RX and TX channel. Just in the PuTTY, I type 192.168.2.1, which is the default IP address, and then accept the connection, and then I get connected to Pluto. The login and password are root and analog. Then here I can see the firmware is successfully set to 0.39. Now I just need to send these commands to change the firmware to behave, to tell the IC now you are 9361, and also enable two RX and TX channel. So I just come here, copy this, then again, copy all these four commands and apply to Pluto, then finally do a reboot. And that's it. When you do that, it changes the firmware, and basically, according to this table, it just now tells the IC now you are AD9361, and also you have two RX and TX channel. Now let's go over the code and see how the beamforming is created. Okay, now let's look at the code. As always, I will upload this code to my GitHub. Please feel free to go and check out the code. I'm going to go over the necessary, important changes compared to single channel transmission, because we have already covered how to configure our ADALM-Pluto and how to send and receive signals in our video about FM modulation and demodulation or a spectrum analyzer. So I'm not going to go over those details anymore. Please go uh, check out other videos as we explore basic and fundamentals behind how to generate baseband signals. But I'm going to highlight what has changed that now we have two TX channels. Basically, one thing we need to do is now, as we connect to our ADALM-Pluto to our TX ADALM-Pluto by ADI.AD9361, we need to add a new command saying SDR underscore TX dot TX underscore enabled underscore channels 0 and 1, meaning that enable both channel 0 and channel 1. Then this enables both of the channels. But also in my RX, because I just only have one channel, I just say channel 0 is enabled. This is the first step that we need to do. Then, as we come down in the code, now that we have two TX channels, we need to provide two different sets of baseband data as we send the data to Pluto by SDR underscore TX, which is our TX SDR.tx. Previously, we would just send one vector of data to this function. Now we need to provide two sets like this. Basically, here we create a baseband form by just first creating a time signal based on our sample rate. Then we create an exponential signal, which is making our I and Q signal by by a tone, which we set here to be 500 kilohertz. Then we pass that to our TX channels, both of our TX channels. The reason for this is that initially we want our TX channels to be identical, but as we want to sweep through the phase to see to change one of the channels phase with respect to the other one, what we need to do is that we change one of the TX channels data. That is done below. If as I come down, some of the codes here are how to calculate half power beam width or FFT of the signal, which I'm going to skip for now to not make this video long. But here you can see this is our main loop in which we sweep phase of one of the channels. Basically, initially we destroy TX buffer because as we have set the TX to be cyclic, it will send same data again and again. So first we need to destroy the buffer, then send a new uh, base information to TX. One channel, channel 0, is unchanged. We send just the same base waveform. But the second one, we just add another argument, multiply that baseband waveform to exponential term, which is e by power of 1j phi, which is basically our phase the phase difference that we want to apply to our baseband. So this phase through this loop is changing by from minus 80 degree to plus 80 degree by steps of 2. So basically each time we just multiply e by power of j current phase to the baseband waveform as we want to send it to the second TX channel. So therefore, channel 0 and channel 1 now will have this amount of phase mismatch between each other. And as we sweep this phase, we want to see how the received amplitude is changing. In this loop, so as we change the TX, we wait for some amount of time for the RX to settle. Then we read RX data, um, deduct its mean from it, basically removing the average of it, then divide it by 2 by power of 11 to make the signal from -1 to +1 because ADALM-Pluto has a 12-bit signed output from ADC. Then we take an FFT because now our tone is at 500 kilohertz. Remember, our TX baseband was at 500 kilohertz. Now our receiver is also at a 500 kilohertz tone. Either we can just look for the amplitude around that 500 kilohertz tone, or just pick the maximum of FFT because we expect to not see other tones in our FFT, just pick the maximum uh, s- uh, and some indexes before and above it, uh, in case, because now we are applying windowing, handing windowing before FFT, we may have some spectral leakage. So we can instead of one sharp pure tone, some of the power of the tone might leak to neighboring frequencies. So basically, we just take a few indexes before and after the maximum and find the maximum, find the power of the signal, then save it into an array as the sweep is going on. So this is the code. I just want to run the code one more time to show you some items as the code is running. We will try to explore the remaining items that are not covered in this video to the next video, because we are going to explore the beamforming um, extensively in future videos as we go on. Okay, so this program uh, has two modes. One is one shot, the other one is continuous. For one shot, if I hit it, it just takes it performs the sweep once and then stops as the sweep is done. So one interesting thing is that you can see this 500 kilohertz tone in our receive FFT, and you can see its amplitude changing as the sweep is being done. One interesting thing was as in the initial phase where the amplitude of the signal was low, these tones here, these non-ideal tones at the FFT, low frequency tones, where their power was comparable to the baseband tones, so we were seeing more them in a larger scale. But as the beamforming continued, so the received power at the receiver increased, this tone became dominant, so the non-ideal tones were not visible. But basically, we have this 500 kilohertz tone. When we perform the sweep, we can see as the phase changes, uh, the frequency, the received power is changing. And what I did to this plot is basically I calculate the half power beamwidth, which is essentially the phase or the degree in which the received power is 3 dB less than the maximum received power. So let's say my maximum is right now at phase of 54 degree. uh, I calculate when I am minus 3 dB below this amplitude, and then based on this, I calculate my delta V, and delta, and from the equations, I can convert this delta V by the frequency and lambda of my operation to the actual spatial uh, uh, degree. Meaning that by using these two TX channels, I'm creating a beam that its half power beamwidth is 57 degree. So this is not a very sharp beam because I'm just using two channels, two TX channels. You can see here as well, but uh, this is definitely showing the beamforming is happening. Uh, but actually we are going to in the future videos we are going to connect both of the ADALM-Plutos to each other using same reference clock to enable actually four channel beamforming and see what happens if we use four channel and how sharper the beam width becomes. Yeah, so because I've covered a lot here in this video, just showing how to configure ADALM-Pluto to enable two-channel beamforming and also two channels and what's the fundamentals behind beamforming. This video is long enough, so I don't want to make it longer. Some of the details uh, 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 I'm not going to go through some of the details in this video, but please tune in because I'm going to explore all the ideas behind beamforming and what we can do now that we have beamforming enabled um, to go explore some more complex and advanced ideas. As always, thanks for watching this video. Please subscribe, share, and comment. Your support means a lot to me. Gives me uh, it gives me the support I needed to continue working on these projects. Thanks.